Research in the atmosphere is a very broad topic, and it encompasses air pollution and weather forecasting, but it also includes details of the atmosphere that very often people are not aware of. For example, the atmosphere is very turbulent near the Earth's surface, and this is the part of the atmosphere that flows past wind turbines. And the turbulence is very important because it helps shape the wind profile, determine how hard the wind is blowing at the top versus the bottom of the turbine. And it's important to understand, but at the same time, because it is turbulent, it is very complicated. And so it remains an unsolved and very challenging atmospheric sciences research problem, and one that has a direct impact on wind energy. So for offshore wind energy, there are really two fundamental challenges, and they're quite related. One is that the science, or the physics, is very complicated. There is motion going on in the atmosphere at scales ranging from storm systems that affect wind power plants down to turbulent eddies that are smaller than the size of a turbine blade, but at the same time affect how the wind flows and around the turbine and how efficient it can be. At the same time, the wind offshore drives the ocean, producing waves that interact with the wind to have various shapes and frequencies. And the wind and the waves together interact or slam into sometimes the structures. And so it's very important to understand the physics of wind energy, both in terms of being able to predict how much power a plant will produce, how reliable it will be, and also how well or what the engineering requirements are so that the turbine can last for 30 years offshore producing electricity. So I mentioned the complexity of the wind turbines.
Yeah.
And that really is the fundamental science challenge, because it's beyond the capacity of current computers to explicitly resolve the physics of all of the processes going on, from storms that may be 1,000 kilometers across to turbulent eddies that may be a meter across. And yet all of those interact with each other in very complicated ways, and we still don't understand all of the ways that happens. So that's a big challenge for understanding how to do that. So one of the ways that we manage that is by making approximations. The scientists will call it parameterizations for the physics that we can't quite resolve in a particular model. The problem with, or the challenge for that at the moment, is that we don't know how best to make those approximations. And in addition, and this is really the other side of the problem, we don't have observations offshore to know whether we're actually doing that right or not. So we take our best ideas from land, and we at present rather hope that they work in the offshore environment, but we don't really know because of a lack of observations. And so the offshore environment with the salt air and the corrosion is a very difficult place to make measurements. But that's one of the big challenges, is to get the observations offshore that we need to know where our physics is wrong and whether we're actually improving it. An example that I think is perhaps useful for wind energy is that of weather forecasting. Many decades ago, when I was a graduate student, the best we could do with with weather forecasting was perhaps a 72-hour forecast. So 24 to 48 hours we felt fairly confident about. 72 hours was kind of hopeful, and beyond that was a roll of the dice. Things have gotten vastly better in weather forecasting, in part because we have made major advances in computation and in understanding the physics, but especially because with satellite technology and other technologies, we are getting observations offshore now, or not offshore, but of the atmosphere, that really constrain the weather forecast models in a way that makes them much more accurate. And now we have some idea that 2 weeks out, we think we might know what's coming. So things have greatly improved because of the observations. The wind energy arena needs that, especially offshore, where the observations in the wind turbine zone, if you will, those heights above the surface are very, very sparse, and we don't have those to constrain the model. So observations are a critical component, along with improving our understanding of the physics. One of the best things that we could do would be to establish a network of offshore observational facilities that could really represent the temperature and the humidity of the entire atmospheric boundary layer, we call it, that the turbines live in, and have those measurements going on under all weather conditions that the turbines are going to experience. That would be one of the very best things that we can do. A second thing would be to continue and expand the collaborative research programs that have been so successful to this point. One of the things that I was proudest of prior to my retirement from the Department of Energy and Pacific Northwest National Laboratory research programs was the Atmosphere to Electrons initiative. And why that was so successful was that it was a collaborative effort that engaged industry. Each researcher, and we encouraged each researcher to not only understand what the problem was that they were trying to solve, but who was going to use their solution and how they would use it. And we engaged industry to make sure that the problems that we were solving were things that they thought were real pressure points for them. And I think that kind of collaborative research effort would be a brilliant use of funding for offshore if it were available. And the other thing that I would say about the level of funding is that putting in a large wind plant offshore is a multi-billion-dollar proposition by the time it's all done. And we're talking about dramatic improvements with millions of dollars, not billions, but millions of dollars in the research arena. And that's a really very small investment with that has a potential for a very large payoff in terms of reducing the uncertainty, reducing insurance costs as a result, increasing the predictability of power that would be produced, and overall reducing the cost of energy. So I think it's very important research, and I think that that would be a very good use of public funds.